Hello everyone, once again I welcome you all to MSB lecture series on transmetal chemistry. In my previous lecture I was discussing about metal-metal multiple bonding. While describing the reason for metal-metal multiple bonding, I also showed you how one can use effectively molecular orbital concept to understand the significance of metal-metal bond and also to understand the magnitude of the metal-metal bond. Let us continue from where I had stopped. Today we shall look into more quadruple bond and quintuple bonding we come across among coordination compounds. I have given here two examples. Look into it carefully. One is a chromium complex and another one is also a chromium complex, but ligands are very different, and you can see in the first one you can see orthometallation is there on opposite side, and you see weak interaction with this phenyl group carbon atom. So, you are having some sort of interaction here, and same thing is true here. So, that means essentially chromium has one ligand, that is a very bulky ligand, and one should remember, if you want to stabilize any metal in its low valent state which is coordinatively unsaturated, only way is you have to do it kinetically. How to do it? You have to go for a very bulky ligand so that it will give umbrella protection surrounding the metal atom, so that it does not give scope for other bigger ligands to enter. So, in this context initially this mono ligated chromium compound was made, and then this interacts two such mono coordinated chromium species, they interact with this ortho substituted carbon here you can see, and as a result what happens, it appears to be having two coordination with almost linear geometry, and in this case what if you carefully count here, we have 5 bonds are there here, and if 5 bonds are there, how to explain that one? Same thing is true in this case also, whereas here nitrogen is there, central pyridine nitrogen is coordinating, and also the nitrogen lone pair is coming here. See, this is the ligand used in case of the first one, and in the second case we have used this ligand here, and you can see here first it binds here, and you will be having almost 1:1 metal to ligand ratio, and then since this side is open, what happens, two such molecules will arrange in such a way that something like this they come and they establish a dimetallic core. So, now we have to explain the origin of 5 bonds in this one. How to do that one? Again we have to go to the same concept that we used earlier to explain multiple bonding, like single bond, double bond, triple bond, or up to 4 bonds or quadruple bond. Same analogy we should use here. One interesting thing is here, in previous case we were just confined to 4 orbitals, that is dz square something like forming sigma bond, and then we had dxz and dyz forming 2 pi bonds, and then we had dxy forming delta bond. 4 orbitals we used. So, 4 orbitals means if the capacity is 8, then you can have bond order 4, but if we want to have bond order of 5 in order to see the formation of quintuple bond, we need 5 electron on each metal d orbitals. That means d5 configuration we had to take in, but in earlier case when we took d5, what happened was 2 electrons were going to delta star. As a result what happens, the bond order was reducing from 4 to 3, but in this case what happens, since it is using sp hybridization, we are left with all the 5 d orbitals for bonding purpose. In square planar complexes we are using dx square minus y square for making metal to ligand bond. You just recall valence bond theory where we are using dsp2 hybridization. That d orbital is dx square minus y square, whereas in this case it undergoes sp hybridization to accommodate 2 ligands surrounding chromium atom. As a result what happens, all d orbitals are left unutilized, and chromium electronic configuration if you see d4s2 or d5s1, and this ligand if you see the top one, if it is monoanionic here through CH activation it forms. So, then it is a monoanionic means oxygen state should be +1, and as a result what happens, chromium will be left with 5 electrons. So, 5 electrons are there and 5 d orbitals are there. Now, that means along with dxy, dx square minus y square also participates in delta bond formation. So, that means now we have one sigma bond through dz square and two pi bonds are there through dxz and dyz, and then we have overlapping of dxy and dx minus y square, that leads to 2 delta bonds. That means 10 electrons are there in the bonding, 10 divided by 2 equals 5. So, bond order is 5. This is how you can visualize quintuple bonding in these kind of compounds. So, that will become clear when we go to the next one. So, I have shown here how it happens. So, next you can see here, this is a compound, another compound here. Of course, here you can see, just go back to this one, and here if the delocalization happens here, of course this is anionic, you should recall here, n 2 are coordinated. So, n minus this is. So, here almost is similar to NH2 minus, I would say NR2 minus. So, now what happens, this is delocalized, as a result becomes monoionic, very similar to couple of ligands I showed you in my earlier class. In couple of examples showed you in my earlier lecture, you can see now anionic it is. So, chromium or molybdenum, they are in +1 state. So, D5 electronic configuration, and how this compound is made, I have given the method here. First you take this compound where chromium is in +2 state, CrCl2 coordinated to 2 neutral ligands such as THF. You take this one and treat this one with lithiated this aromatic group, and once you lithiated this one is there, LiCl comes out and you left with one Cl here. As a result, what happens, it forms a dimeric structure having 2 chloro bridges here, and now this one needs reduction. For that one, Kc8 potassium over graphite is taken, slight excess in THF, then it will abstract 2 chlorides to generate chromium 1 species from chromium 2, and then now chromium 1 species is coordinatively unsaturated, it interacts with this carbon here, and then it establishes like a bidentate mode of coordination having this kind of structure. And you should remember that here we have 5 electrons are there in the d orbit. So, this was reported in 2014 in Dalton transaction. So, another compound is there. I will give you the preparation of this compound also before I proceed to show the MO diagram to confirm the presence of 5 bonds. So, in this one to take, it is already quadruply bonded compound, very similar to rhenium dimer Re2Cl8 minus. So, just look into this one. So, this is a potassium salt because tetraanionic. So, what one should do is you add a ligand, that ligand I will show you what it is, and then you can make a compound of this type here. I will show you what is A, and then again you use the reduction process using potassium over graphite, that leads to the formation of a quintuply bonded compound like this. So, you may be wondering what is A. So, A is this one here, lithiated, this bulky aromatic compound here, this is the lithiated one. And then if you just see here 2 lithiums here, 2 lithiums are there, that means when you are using 2 equivalent, 1 lithium is coming out as LiCl. So, you can see the missing of 1 chlorine here, and then another one will remain here coordinated to lone pairs on chlorine here. And then of course, once when you reduce with Kc8, everything is gone and you simply ended up with a molybdenum +1 compound having this monoanionic ligands bridging in this fashion. I am sure it is clear about preparative methods. So, this came in 2009 in JOGS. So, now just see here molybdenum is +1 state D5 system. To form this complex, as I mentioned earlier, molybdenum has not used dx minus y square, otherwise it would have used if it had square planar geometry. So, now this is also available along with the dxy, oriented in this fashion, something like this. One is like this and another one is at 45 degrees. Both of them can only overlap in this fashion when they stacked in along z axis. You can see here 5 are there. Now, just see, I have added dx minus y square also for this bonding scheme here. We have total 5 electrons, whether you take chromium or molybdenum. First 2 establish a sigma bond by utilizing 2 electrons, and now pi bond we are using these two 4 electrons. So, 2 pi bonds are there, and now we are using now 2 electrons here, one each from dxy and dxy square from both the metal centers, and then we establish a 2 delta bond. So, then the bond order is 5. So, this is how you can explain quintuple bonding among coordination compounds having d5 electronic configuration with dx square minus y square available for metal-metal bonding. Now, let us go to another interesting compound here. If you recall my previous lecture where I classified metal-metal bonding compounds into covalent bonding, dative bonding and symmetric metal-metal bonding. So, now let us look into dative bond scheme. So, when a metal with at least 2 d electrons and a moderately high electron count is adjacent to a metal that is coordinatively unsaturated and electron deficient, in that case what happens, both of them can have some sort of Lewis acid base interaction. The one metal that is electron rich can give a pair of electron to the one which is electron deficient, provided it has empty orbitals of suitable symmetry to take those electrons. In that case what happens, you can establish a dative metal-metal bond, or you can call it as a adduct between 2 metal centers. So, I have given one ideal example here, and it is very interesting to analyze this one, and there are several ways one can analyze this compound. This is a phosphide ligand here, you can see Pr2 minus, and it is also Pr2 minus, and we have 3 carbonyl groups altogether. And if you just look into this one, well, of course, this can be +2 state, nickel can be +2 state provided it anionic establishes a bond with nickel. In that case what happens, this will be +2 state, that means D8 system, D8 plus 4 12 and plus 14. So, this becomes a 14 electron species. On the other hand, this one is nickel 0, now Pr2 acting as a neutral ligand towards this nickel. So, D10 plus 8 it is 18 electron system, that means it is very similar to NiCO4 or NiPPH3 4 times. Now, so this is 18 and this is 14. So, these electrons can go here, so that it becomes a 16 electron species, and to an extent electron deficiency can be removed here. So, you can see how dative bond is directed from this coordinatively saturated and electronically rich nickel to this 14 electron species. Okay, that means what are the other alternates? For example, we can have phosphide 1 each on these 2 metals. In that case what happens, both of them will be nickel +1 state. If they are in nickel +1 state, what happens, the D9 system they become, both of them become D9 system, and then we have anionic on both sides. So, 2 electrons are coming here and bridging one neutral, also 2 electrons are coming, whereas in this case 1 carbon monoxide is there, and of course there is one metal-metal bond you can think of, D9 system. So, 16 electrons will be there for this one, and then here in +1 state, and then you have 4 electrons, this will be 18 electron. But here if it is 16, many D8 systems are stable with 16 electron species, you cannot think of a dative bond. So, since it is an example that is proved through experiments and also X-ray structure, so this kind of analysis is incorrect. So, nickel +1 is not correct, instead what I said earlier. So, this is in 0 state and this is in +2 state is the correct analysis, and nickel with 18 electron is donating 2 electrons to this one. So, let us analyze for better understanding. So, now you can see here 2 options. So, now I have shown both the terms here. So, I have shown here nickel, this is binding to 4 neutral ligands with 18 electrons with D10 system, that is 0, and now this is going this way. That means now this is in nickel +2, because here we are talking about phosphide anionic. So, this is a covalent bond and this is a coordinate bond. Now, this is in nickel +2 and 16 electron species, and now this will be nickel 0. So, this also becomes 10 plus 16 electron species, both are 16 electron species. In that case what happens, none of them can give electrons to this. On the other hand, other alternative is, as I mentioned, nickel 1 can be there. Again we overruled from my previous discussion and argument, and then what would happen here, 17 and 18. and now it is 16 and 18. But when we looked into the X-ray data, what it shows is nickel 2 NiCO 170 picometer and Ni2 phosphorus 216 picometer. Now let us look into the bond parameter for this one, nickel 0 NiCO 178 picometer. That means it is longer. Why it is longer? Because it is taking some back bonding is there, because it is electron rich. When the back bonding is more to CO, what will happen? NiCO bond shrinks and CO bond distance increases. So here it is electron deficient, it is not readily donate electrons to pi star of CO. As a result, what happens? NiC bond is little longer, as a result CO bond still has triple bond character, so it is slightly shorter. So that means this proves that this is in +2 state and this is in 0 valent state, and again that is also reflected from NiP 224 picometer. This is a coordinate bond, whereas here we have a covalent bond because it is an anionic P minus. So 216, this is shorter, always covalent bonds are shorter compared to coordinate bond. So this is another proof to say that this has a dative bond with nickel 0 18 electron species and nickel 2 14 electron species. So this proves beyond any doubt that there is a dative bond between two nickels, and this 0 valent nickel is donating a pair of electrons to this one to overcome its electron deficiency. This is how one should analyze carefully by looking into all parameters, and Ni distance is 241 picometer or 2.41 angstrom units. So now let us come to the last one. I did mention about symmetry metal-metal bonding. So what would happen here is weak metal-metal interactions observed due to the molecular orbital symmetry interactions of filled and empty metal-metal bonding orbitals and or antibonding orbitals observed in D8 system and is very rare. D8 system should not have any metal-metal bonding due to the 0 bond energy, as both bonding and antibonding orbitals are completely filled. That means you can see here, for example, if you recall MO diagram, just I am writing here 2 electron sigma, 2 pi here and 2 delta, and then again delta is filled and pi is filled, and then sigma is filled. So this is sigma 2 pi and then delta, delta star, pi star, 2 pi star and sigma star. So all 10 electrons are there. So bond order is 0. So that means you do not expect any metal-metal bonding in a square planar complex having D8 system, but HP Gray and others observed in a few bi or polymetallic complexes having D8 electronic configuration and showed the presence of weak metal-metal interactions both in solution and in the solid state. That means if you observe in solution these molecules retaining weak interactions and stacking along the axial position, probably there is bonding that has to be explained. So one such complex of iridium with isocyanate showed weak metal-metal interactions, and that gave enough proof to go further. You can see here this iridium complex here, iridium plus compound D8 system having neutral isocyanate ligands are stacked up in this fashion, having unusually shorter iridium-iridium bond. Despite overrule, we overrule any metal-metal bonding as bond order comes to 0. Then how to explain this one? So Gray proposed in 1974 that these weak metal-metal interactions were caused by a molecular orbital symmetry interaction between the filled sigma metal-metal bonding and sigma star anti-bonding orbitals with the empty pz sigma and sigma star orbitals. You should remember, when we think of valence bond theory to explain square planar complex geometries, we are using DSP2. That means d orbital is dx minus y square, and then we are using s orbital along with px and py orbitals, and pz orbital is left unutilized in a square planar complex along with 4 other orbitals, but in D8 what happens, everything is filled. That means now the interaction between dz square, where we have sigma and sigma star filled and unfilled, they interact with empty sigma and sigma star of pz orbitals. That means take pz orbitals from 2 metal centers and try to establish a molecular orbital sigma pz and sigma star pz, and then they are empty, and whereas this is filled, that means there is some interaction happens between these two pair of molecular orbitals, the filled dz square bonding and antibonding orbitals with empty pz. Due to this kind of interactions, the empty orbitals are pushed up in energy and the filled orbitals pushed down in energy by this symmetry interaction. So, due to this kind of arrangement, this generates a weak metal-metal bond strong enough to allow these complexes to form MM bonds and retain them even in solution. So, this was observed in many complexes of iridium and even palladium and platinum compounds with the D8 electronic configuration. Probably if you look into literature and work by Gray, you will come across more examples. With this, I am completing the discussion on metal-metal multiple bonding. So, once this is done, you should remember one thing: when we predict metal-metal bonding in these cases where you can have single bond, double bond, triple bond, quadruple bond or to quintuple bonding, the concept used is very different compared to what we come across in predicting metal-metal bondings while using 18 electron rule. Sometime they may be, in some cases it does not apply. Do not try to mix up, they are different entities and different type of compounds we come across these things. Maybe there may be some examples where we can see both merging to give a correct explanation about 18 electron rule. Nevertheless, they are entities, but beautiful concepts, and without any problem one can explain using simple molecular orbital concept. What one should remember is, again, in case of square planar complexes, we have 4 d orbitals are there: dz square, dxy, dxz and dyz, and dxz and dyz generate 2 pi bonds, dz square generates 1 sigma bond, and because of their orientation dxy will overlap only like this, and they generate delta bonding. And then we have 8 electrons in the bonding, and if bond order is nothing but number of electrons present in bonding orbitals minus number of electrons present in the antibonding divided by 2. So, that gives the bond magnitude of 4. To have 4 bonds or quadruple bond, so a square planar metal complex should have d4 electronic configuration, or they should have 4 electrons in their d orbitals. And if we have unutilized dx minus y square also with lower symmetry or sp hybridization, for example, in that case what happens, dx square minus y square is also made available for bonding. In that case all 5 d orbitals are available for bonding. You can imagine or you can explain the quintuple bonding. There may be more examples. Of course, if you are more interested, you can always go to literature and look into more examples. In my next lecture, I shall discuss about the preparation of some of the important coordination compounds and organometallic compounds, keeping their utility in further reactions and then making ideal compounds for homogeneous catalysis. Until then, have an excellent time reading chemistry.